Welcome to Maths with EJD. In the past few videos, I've been talking about applications of differentiation. I've talked about three different applications, starting from kinematics to linear approximation to rate of change. And now I come to the last part. Of course, that doesn't mean that there are no other applications of differentiation. There are so many more, but these are like the key ones. So this is the last video on applications of differentiation, and it is focusing on stationary and turning points. Now, the question is, what are stationary points? You remember under kinematics, right? I told you that in projectile motion, for instance, if you throw a ball from a height or from ground or wherever you throw it from, you just release it into the air like that. It gets to a maximum height and it stops momentarily before coming down. That point where it stops, you say, you called it the maximum point, right? That's like some kind of stationary point where it turns. So it's going up and then it gets to that height, stops momentarily and starts coming down. So that's a very good example of stationary or turning point. So the idea of projectile, you have something thrown up, then it reaches a maximum height and then it starts coming back down. So this is a turning point, a stationary point, or call it turning point. Turning point. Some people can call that extreme point, and so on and so forth. So all kinds of names for that, meaning the same thing. All right. So stationary points are of three basic forms. They are minimum, maximum, or inflection points. They are minimum, maximum, or inflection points. And the stationary or turning point of a function f of x is the point where its derivative is zero. That is, f prime of x is equal to zero. Now, you discover that when we're solving problems under kinematics, right? If you are told to find the time it takes to reach the maximum height, you know already that the time it's at maximum height, right? Velocity is momentarily zero. So if you want to find that, it means you have to differentiate your displacement and equate it to get velocity. Then you equate to zero. So from there, you can get the time it takes to reach that height. So that's the kind of thing that is happening here. So at stationary point, the velocity is equal to zero. That means the derivative is equal to zero. And then a stationary point can either be a minimum, maximum, or inflection point. So in the typical example of a graph, right, you have a graph this way, and then let's say you have something like this and like this. So this is a very good example of a maximum point. So this is a very good example of a maximum point, this point right here. And this one down here is like a very good example of a minimum point, right? This is a very good example of a minimum point. And the inflection point is the point where, this is maximum, right? Then it starts turning and then it goes minimum and like this. So somewhere around here is what you call the inflection point. And they have their mathematical notations, as we're going to see pretty soon. So that's the kind of thing we'll be dealing with. Okay, look at this. Now, this gives you a kind of a systematization of what exactly you need to do with stationary points. So these are the steps for finding stationary or turning points. So the first thing is to find the stationary or turning point for a function f of x. The first thing you do is differentiate. You differentiate to get f prime of x. After you get f prime of x, right, then you solve f prime of x equals zero. You equate that derivative to zero and solve. Then you're going to get values, just like what you did in the case of kinematics. When you solved, you got the time, or you get the independent variable or the possible values of that. So solve f prime of x equals zero and substitute the obtained values of x into f of x to obtain the stationary points. That's one thing. So solve for this, you get some values of x. Then now put the values of x back into the original f of x you have. Because, on the graph, right, you need for you to get a point, you need both the x and y axis. So by solving this now, you're going to get maybe one or two values of x. So you have to substitute those two values of x back here to get the corresponding values of y for those x's. Then the next thing is you derive f prime of x by differentiating f prime of x one next level, right? And then you now evaluate f prime of x for each of the stationary points to determine if they are minimum or maximum point. There are already rules to determine whether they are minimum or maximum points, as we see. Given that the stationary points x equals x star, so this x star is any value you get by solving f prime of x equals zero is actually an x star. So if you put that x star into your f prime of x, which you get here, then it means you are evaluating something like f prime of x star. So if that f prime of x star is less than zero, Less than 0 means it's maximum point. So you can see it looks kind of contradictory, but that's the idea. So if by the time you put the value of x you got from here, from here into this, and it's negative, less than 0, then you are dealing with so that value of x corresponds to the maximum point. Then, while if you do f prime prime of x star and it's greater than 0, that means you are dealing with a minimum point. Okay. But of course, if you also want to talk about inflection points, all you need to do there is you now solve f prime prime of x equals 0, like you solved f prime of x equals 0 before. So you solve f prime prime of x equals 0 to find the inflection points. So those are the steps we need to take. Okay, so let's look at actual examples of this. So we have first one says find the stationary points, or I can say find the turning points, or find the maximum, minimum, and inflection points of this function f of x, which is 1 over 3x cubed plus 2x squared minus 5x plus 1. So f of x, of course, is already this 1 over 3x cubed plus 2x squared minus 5x plus 1. The first thing I told you to do is differentiate it. You have f prime of x. 1 over 3x cubed is 1 over 3 times 3x squared. 1 over 3 times 3 is 1. So you have x squared left, and you have 2x squared, differentiate, you get 4x minus 5x, you get minus 5 plus 1, that's 0 because it's constant. So you have found, you have differentiated. The next thing I told you to do is to equate that to 0. So, and you can see f prime of x, which is x squared plus 4x minus 5, you can factorize it into x minus 1 into x plus 5 and equate to 0. So from here now you can already see that so you can have x minus 1, x minus 1 equals 0, or x plus 5 equals 0. When x minus 1 equals 0, that means x equals 1. So that's why you have x1 star equals 0 and x2 star equals minus 5. Now, when you equate the derivative to 0 and you solve, that is what it's called in dynamical systems. It's called equilibrium points, or stationary points, or steady state. So these are like the steady states now, because at that point there's no motion, there's momentary stop. So, and that happens at x1 star equals 1 and x2 star equals minus 5. Okay, that's the next step. So the next thing you want to do is you want to check the nature of x1 star or x2 star, whether it's maximum or minimum. And the way to do that is to differentiate this derivative again. So to find the nature of the turning of the points, we have f prime prime of x, which is differentiate this, x squared, that's 2x, 4x, that's 4, minus 5, that's 0. So to find the nature of the points, well, we have f prime prime of x equals 2x plus 4. So that now you can now put x1 star. So f prime prime of x1 star, which is the same thing as f prime prime of 1. x1 star is 1. So that's 2 times 1 plus 4. 2 times 1 is 2 plus 4. That's 6. 6 is greater than 0. That's positive. So which indicates that this value 1 corresponds with a minimum point, because it's for 6 greater than 0, that's positive. Positive value of f prime prime of x star corresponds with minimum point. Okay, on the other hand, you have f prime of x2 star. So that means f prime prime of minus 5, and that is equal to 2 into minus 5. 2 into minus 5 is minus 10. Minus 10 plus 4 is minus 6. Now you have minus 6 less than 0, which indicates a maximum point. So you see 1 corresponds with minimum point and minus 5 corresponds with maximum point. So that's not all. You can't talk about a point by just talking about only the x, right? So you need to get the full gist. You need to take these values of x back into the original function to get the corresponding y1 star and y2 star. But for now, we know that 1 is a minimum point and minus 5 is a maximum point. So let's go on to take care of that. Okay, good. Now, because you need to know the x and y components, right? So you go back to the original expression, f of x, that's now 1, f of 1. So you have 1 over 3 into 1 cubed plus 2 into 1 squared minus 5 times 1 plus 1. So that will give you 1 over 3. This is 1 over 3. This is 2. This is minus 5 plus 1. If you evaluate all that, you get minus 5 over 3. So you see that the minimum points, since you have established that 1 corresponds with minimum point, so this is your minimum point now. So that means that on a graph, this is what it is going to look like. You have x is 1, right? And y is like minus 5.3. That's minus 1 point something. So maybe it's somewhere around here. So you have, something around here, and it's minimum. So minimum is facing up, like will face up like this. It's going like up this way. And then the next one, you put -5 into the expression. You have 1/3 into -5 cubed plus 2 into -5 squared minus 5 into -5 plus 1. So here, -5 raised to power 3 is -125 divided by 3. -5 squared is 25 times 2, that's plus 50. -5 times -5 is plus 25, and then you have plus 1. So you have 103/3. So again, you see the maximum point now is -5 and 103 divided by 3. So that means you have it, let's say you have -5 around somewhere here, and then you have 103/3 somewhere. So this is like your maximum point. So this is like this. So you see, this one is minimum, this is maximum. So you can try to join things up like this. So this is what the curve looks like. So if you want to do some kind of curve sketching, so this is where you have 1 comma -5/3, and then this is where you have -5 comma 103/3. That's like your maximum point. Okay. So finally, if you want to find the inflection point, to find the inflection point, you solve the second derivative. So yeah, which is f prime prime of x equals 2x plus 4. Equals 2x plus 4, which is equal to 0. That implies that 2x equals -4, and then divide both sides by 2. 2x equals -4, and divide both sides by 2. So 2 cancels to 2 here is 1, 2 here is 2. So that's why x is -2. So the inflection point, now you see the inflection point is somewhere around here, -2. So, but of course, the point is not complete until you know the y-axis. So put -2 also in the original expression. So you have 1/3 into -2 cubed plus 2 into -2 squared minus 5 into -2 plus 1. So -2 raised to power 3 is -8. You have -8/3. -2 squared is 4 times 2, that's 8. -5 times -2 is plus 10 plus 1. Evaluate all that, you get 49/3. So -2, 49/3, that's the inflection point. And usually inflection point is that confusion between maximum and minimum, that mid path. So if this is -2, and then 49/3 is something like 16 point something. So let's say this is 16 points. This is 49/3 in short here. So it means your inflection point is somewhere around here. I want to change the marker so you can see what I'm talking about. All right. Okay, so this is like your inflection points. Maybe not accurate, but at least that's an idea of what is expected. So you can use the idea of stationary points for curve sketching. So you can see what the curve looks like, right? This is the curve put in decimals. So you can see the graph of f of x equals 1/3x cubed plus 2x squared minus 5x plus 1, with the maximum point a -5, 103/3. You have the inflection point here, which is -2, 49/3, and you have the minimum point, which is that is 1, -5/3. So, and that's how that goes. So, I mean, it's so interesting. Now you can use this kind of idea to, for maybe in business cases, like for business mathematics, right? You want to make some decisions. So all the maximum points, minimum points, and all these things, they can correspond to maybe the maximum profit you make from a business, or the minimum production cost and things like that, depending on the situation you have. So that's why I've decided to bring you this practical example, so you can see how that applies maybe in business, and it applies in different areas like pharmacies, pharmaceutical industry, where you need to measure the dosage of drug that will work for a particular situation. Okay. So example 2, we have this, that a wristwatch company has the records of quantity of watches produced and cost of production and revenue are as shown in the table below. So you have the quantity produced. So in times 1,000, right? So this is 3,000, this is 2,000, this is 4,000, this is 1,000, this is 2,000, like that. And then you have the cost of production is 5 million naira. Maybe it's some high-end watch or something like that, 5 million naira, 3 million naira, 3 million naira for producing this, for 2 million for producing, 3 million for producing. And the revenues, like after production cost, right? After then they now sell. So what you made using 5 million naira, you now sell for 7 million naira, 4 million, 3 million, 3 million, 5 million, and so on and so forth, right? So the question is asking, obtain the cubic polynomial costs and revenue functions in terms of the quantities of wristwatches produced. So now this is specific, cubic polynomial. So that means we need a third order expression for that. Then derive the profit function. Of course, we already know that profit is revenue minus production, revenue minus cost, right? That's profit. Then the next thing is we need to find the maximum profit the company can make. the maximum profit the company can make. And all of that can come from this our idea of maximum, minimum, and stationary and maximum, minimum, and inflection points. So let's go into that. So the first thing I did here is this. One other tool I like to use a lot is Wolfram Alpha. Wolframalpha.com. It's online. Just type Wolfram Alpha, you find it. Wolframalpha.com. So you can put all the data I gave you. You can pair the quantity produced and the production cost. You can pair them together, and to give you a third order equation, just say you want cubic feet. It will give it to you, and maybe you have other devices. So what I just did is I fit in the Q and C. That is the quantity produced and the cost of production. So data to a cubic polynomial, we have the cost function to be minus 1.1 q cubed plus 7.5 q squared minus 14.4 q plus 10. Then fitting the QR, that is the quantity produced with the revenue, data to a cubic polynomial. We have this revenue function that is minus 1.3 q cubed plus 8.0 q squared minus 13.8 q plus 10. Or even if you don't fit it yourself, maybe you have a question and you have these formulas already. The profit function is simple. The profit as a function of quantity is simply revenue as function of quantity minus cost as a function of quantity. And you already know R, this is it. It's here. Minus this. So when you do that, minus 1.3 cube minus 1.1 cube, that's minus 0.2 cube. Then 8 minus 7.5, that's 0.5 q squared. Then minus 13.8 q, minus 14.4 cube, that's 0.6 cube. And then you have 10 as the constant. So 10 minus 10 just simply goes to 0. So this is your profit function in short. And now that you have the profit function, the next question is to find the maximum profit, I believe. So to find the maximum profit, you already know what to do. It's like you're looking for a stationary point, okay? But here we are just generally looking for maximum and minimum profit. So to find the maximum profit, the first thing you want to do is differentiate the profit function. The profit function is minus 0.2 q cube. So that's minus 0.2 times 3. That's why you have minus 0.6 q squared. Then when you differentiate that, then 0.5 q squared, that is simply 1 q. 1 q, when you differentiate 0.5 times 2, that's 1. Then the power of 2 reduces to 1. So you have just ordinary q. And then for 0.6 q, you just have 0.6 q equals 0. So we want to solve this now. And one of the things we can do, we can simply use our formula method. So this is the minus 0.6 is a, b is 1, which is the coefficient of q, and c is 0.6. So we have minus b plus or minus b squared, that's 1, minus 4 into a, 0.6, and c, 0.6, all over 2 times a, that's 2 into 2 into minus 0.6, like that. So we just tidy things up. So this is this one here is minus 1 here, plus or minus. Then you have 1 squared is 1. Then minus times minus is plus also. 4 times 0.6 times 0.6 is 0.36. Multiplied by 4, you have 1.44. So if you add that together, 1.1 plus 1.44, that's 2.44. So you have minus 1 plus or minus square root of 2.44 divided by minus 1.2. So now you have square root of 2.44 is 1.56. So minus 1 minus 1.56 divided by minus 1.2, you get minus 0.47. And then minus 1 plus 1.56, that will be 0.56 divided by minus 1.2. So altogether, you have minus 0.47 and 2.13. And of course, since quantity cannot be negative, so it means we are going with Q2, which is the positive quantity. We cannot have negative quantity, like that. Okay, yeah, we got this from the first one, right? Minus 1 minus 1.56 divided by minus 1.2. So that's minus 2.56 divided by minus 1.2. I believe that's where we got this 2.13 from. So the other one is minus 1 plus 1.56. So the plus comes first. That's why the answer is negative. For the plus, you have minus 1 plus that. That's 0.56. So that's negative. For the that's negative. So, but if you have minus, divide by minus, you have the positive, which is Q2, which is 2.13. Okay. So the next thing is we want to find the nature of the points. Of course, maybe this is just for the fun of it, because normally we know already that we cannot be working with negative quantity. But I mean, just to satisfy our conscience, that's why we are doing this. So to find the nature of the points, we have P prime prime of Q. That means you differentiate the what you have differentiated already, differentiate again. That's minus 0.6 Q squared. That's minus 1.2 Q, then plus 1. This is 0. So we have minus 1.2 Q plus 1, such that P prime prime of minus 0.47, that's minus 1.2 times 0.4 minus 0.47 plus 1. You get all this, and this is greater than 0, which indicates you have a minimum point. Don't forget, we are looking for maximum profit. So even if this is a good answer, we won't take it because we need the maximum profit. Because when you do business, you need maximum profit. So then if you put P prime prime of 2.13 into the same expression, you have minus 1.2 plus 2.13 plus 1. So you get minus 2.556 plus 1. And that is minus 1.556 less than 0, which indicates maximum profit. And for you to find the maximum profit now, it means you're going to use Q, which is 2.13, put it in the original expression. The original expression was minus 0.2 QQ plus 0.5 Q squared plus 0.6 Q. So now we have minus 0.2, 2.13 Q plus 0.5, 2.13 squared plus 0.6, 2.13. When you evaluate all that, you get 1.62. So that means that 2.13 times 1,000. So for you to make maximum profit, you need to make 2.13 times 1,000. You know, the wristwatches are in thousands. So 2.13 times 1,000. So you need to make 2,130 wristwatches, all right, which should be produced in order to generate the maximum profit. And the maximum profit is 1.62 million. So 1.62 million, that's 1,620,000. So that's a very practical example for you to play with. Okay, I think I forgot to show you exercises the other time for apart from kinematics. I forgot to show you exercise for linear approximation. I hope I hope you follow this video down here so you can also see. So these are exercises for, okay, let me show all of them. Kinematics, so examples for kinematics. Then these are examples for linear approximation. So try your hands on this. Find the linear approximation of the following. Then these are examples for rates of change. Good examples to try your hands on. And these are examples for stationary and turning points. So with something practical even right there that you can try. So I've told you again, you can feed the data to a cubic polynomial to get physics scores as a function of mathematics scores using something like Wolfram alpha, like I've told you. So, and these are exercises. So, okay, this is the Wolfram alpha I told you about. Then I always use Desmos for graphing. Then this is a very good book on calculus. So if you have not signed up to this channel, please make sure you do that so you can always get other videos that will come after now. Thank you. See you in the next video.